Okay, so in this video, we're going to examine Newton's first law of motion. And Newton thought a lot about motion and what caused objects to move in the way that they move. So we've examined what it looks like when objects travel with a constant velocity, and we've looked at what objects look like when they travel with acceleration. And what Newton was trying to do was to connect together. Why do some objects travel at a constant speed while some objects change their speed, speed up or slow down, or they turn? And what he realized, partially through experimentation, but partially just through mental exercise, he was able to overcome the common misconception about objects. And that common misconception is that objects' natural state, that they want to be at rest, that all objects want to come to a stop. For example, if we take a car, a little toy car, and I give it a push across the table, it comes to a stop. And I'm sure you can think of thousands of examples that you've seen where something eventually just came to a stop. It seems natural that that's what it wants to do. But what Newton realized that when you really analyze the situation, that's actually not the natural state of objects to be at rest. The natural state of objects is to keep doing what they were already doing. Now, if they were already at rest, then yes, they will stay at rest. But an object that is in motion, it wants to stay in motion. It naturally wants to keep moving, and it requires you to unbalance the forces acting on it in order to get it to come to a stop. So we're going to go through how Newton phrased the first law, and then I'll give you maybe a little cleaner, a little more concise version of the first law. And we'll explain what this term inertia means. The first law is usually referred to as the law of inertia. And what Newton said about objects was that if an object was at rest, then it will remain at rest. And if the object was in motion, it will remain in motion at a constant speed in a straight line. Now you may see this word body appears frequently, and that's just the way in that time that they would refer to an object that had mass. So anything could be a body. The little toy car, this pen is a body, I'm a body, the earth is a body, the sun. Our galaxy could be a body. It could be a little molecule of air flying across the room. Anything could be a body as long as it has mass. And what is going to happen with any object that has mass is that if it was at rest, it's going to remain at rest. And if it was moving, then it's going to keep moving at the same speed in a straight line unless you act on it by a net force. And what that net force means is if you add up all the force, or we'll put in parentheses, the total force. So you may have some forces that are pointing to the right and some forces are pointing to the left. So you have some positive forces, you have some negative forces, they're working against each other. If they add up to be zero, then what's going to happen is the object is going to continue to do exactly what it was doing. So what that says is that if the net force equals zero, then we will have constant velocity. Now, it might seem like what Newton was talking about was two different things because he said objects at rest remain at rest and objects in motion remain in motion. But actually, those are the same thing because an object like this car at rest is traveling with constant velocity. It is traveling at the same speed in a straight line. It just happens to be that that speed is zero. It's just sort of a special case of constant velocity. But it's really no different. This was the great revelation that Newton had. It's really no different than when the car is traveling at a constant velocity. What he was trying to say is that the reason why objects travel with constant velocity in our everyday world is because the forces have come together in balance, and when they are balanced like that, then the car just continues to do whatever it was doing. It's as though it doesn't even notice those forces acting on it. So when I push on the car, I apply a force this way, there's a little bit of frictional force this way, and that's what causes the car to travel at a constant speed as I push it across. Now that's, really kind of goes against some people's, what I would say is common sense, because the friction really throws a wrench in the works. And it's very difficult for people to conceive of situations where there's no friction and what would happen to an object if there really was no friction. Well, the best example is to think about what it's like in outer space where there's no air, there's nothing. There are little small particles here and there, but for the most part, there's basically nothing there. So when we send a spacecraft and we launch it out towards the outer solar system, that spacecraft, if it's given enough speed, will just exit away from the sun and escape the sun's gravity and continue to travel in a straight line at that speed forever until it runs into something. Maybe a little bit closer to home, you might think of an air hockey table. So in an air hockey table, essentially by having the puck move on a sort of a pillow of air, takes away almost all the friction because the surfaces no longer push against each other like they do for this toy car. And so if you imagine a very long air hockey table and we took that puck and we just slid the puck away, the puck would just continue to move away without any further pushing. There's no engine on the thing. The puck would just continue to move forever until it just disappeared off into the distance. So because people live in a world that is complicated by friction, it makes it seem like that's the natural state of objects, is to objects want to eventually come to a stop, but they really don't. The reason why they come to a stop is because outside forces, friction is an outside force. That outside force acts on the object to take away its velocity. So the basic idea behind the first law could really be summarized maybe a little bit more concisely by just simply saying that a body will remain in constant velocity unless it's acted on by an unbalanced force, or you can also say if it's acted on by a net force. So when the forces are balanced, then we get constant velocity. And you can imagine then, obviously, when the forces are unbalanced, we'll have acceleration, and that's what the second law is all about. So the idea behind the first law is that we get constant velocity when we add up the net force. So we look at all the forces that are acting on an object, and make sure to identify every single force. And when we add up all those forces and they add up to 0, then the result will be that the car will travel with a constant velocity. Now, you won't know what that velocity is necessarily because the law doesn't tell you what velocity you'll have. So a car traveling at 5 miles per hour has a 0 net force acting on it. A car traveling at 150 miles per hour also has no net force acting on it as long as it travels with constant velocity. And what that means for the car is that the thrust force must be equal to the drag and the friction, and when that occurs, then you travel with constant velocity. If the thrust wins, it's unbalanced in the direction of the thrust, then you speed up. If it's unbalanced in the direction of the friction or the drag, then you slow down. So we'll look at the accelerated motion when we talk about the second law, but part of the idea behind what Newton was trying to convey, this may seem like it's not very much of an equation. You just add up the forces, and what you know is that they add up to 0. But conceptually, there is really kind of an important idea, and that is that objects resist changing what they're doing. That's the natural state of the universe. Objects want to continue to do whatever they're doing. And if that means being at rest, then they will stay at rest. But their natural state is if they are moving, they want to keep moving, and they're only going to stop if the forces become unbalanced or if there becomes a net force. But when there is no net force, then that object just continues doing whatever it was doing. That property of resistance, that things that makes objects so resistant to changing what they're doing, Newton coined the term inertia for that. So for all practical purposes, when you talk about an object moving in a straight line, the inertia is based only on their mass. Now, if you have an object that's spinning or rotating in some direction, then the inertia, there's a little bit of a different way to calculate the inertia. But we're going to just be looking at objects moving in a straight line. And for objects that move in a straight line, the measure of inertia is how much mass you have. So if you have more mass, you have more inertia. That means that you are more resistant to changes. Those changes could be speeding up. It will be more difficult to speed you up if you have more mass. It will be more difficult to stop you. I think if you've ever driven before and you've been in a heavy car, you can really feel it's more difficult to bring that car or that vehicle to a stop. And then the third thing is it will be more difficult for you to turn. And so that's really a great example historically is the Titanic. So the Titanic, which was an enormous ocean liner, spotted an iceberg, but with only a little bit of time. They had something like around 900 feet to make the turn or to try to come to a stop. Unfortunately, the Titanic required a mile to bring the ship to a stop because the ship has so much mass that even though it has very powerful engines, still with that much mass, it's really difficult to bring it to a stop or to bring it up to speed. It takes a long time to speed up and to slow down. But in this case, they were trying to turn, and they had about 37 seconds to get the ship turned and point away from an object that was probably only maybe 200 or 300 feet across. So while it's large, it's not like it's trying to miss a mountain or something like that. The portion of it that they were that was endangering them was only maybe a few hundred feet across, and they still could not turn that ship in time. Another great example would be trains. Trains require enormous amounts of distances to come to a stop, and they take enormous distances to come up to speed because they have so much mass. These are some of the heaviest objects that we put in motion, and as a result, they are very difficult to speed up and slow down. Oftentimes, cars get hit in the train crossings. They get stuck on the train crossing, and even though the train may see them a mile ahead of time, they still oftentimes cannot stop, even by putting all the brakes on. They may take up to a mile to bring the thing to a stop as a result of the fact that they have so much mass. The last thing I just want to point out about the first law before we look at some of the examples is there's a term for when the forces are balanced, and this term should really make sense. That is that the term equilibrium, to say that the two forces are equal to each other, or maybe there's more than two forces. Maybe there's 3 or 4 or 5 forces. The positive forces, and you add up the negative forces, and they add up to 0, then that object is said to be in equilibrium. So that's going to be really important. We're going to look at this in the first example problem. We're going to try to achieve equilibrium, and when you are told that an object is either in equilibrium or that you want to make the object be in equilibrium, then what you know is that the forces must add up to 0. The only way an object could be in equilibrium is if all the forces add up to 0. So let's take a look at an example problem. We'll look at 2 example problems. So let's keep it really simple in the beginning here, and let's just look at a tug of war. So we don't need to worry about what the names of the forces or anything are. The names of the forces are from the 4 people: Steve, Sally, Jamie, and Jose. But we don't need to give names like thrust or drag or anything like that. What we essentially have is a rope. I'm going to use the center of mass of the rope to think about the forces that are acting on it. So I'm going to make a little free body diagram, and then I'm going to create the equation that explains what's going to happen to this rope. So the first 2 people, Steve and Sally, they are both exerting a force to the left. Steve with 450. So I'm going to make a pretty long arrow for Steve. So 450 to the left. Sally also exerts her force to the left. So I'm going to draw another arrow, but I'm going to make it a little bit shorter. A little bit shorter than that arrow. Then on the right side of it, you have 2 people. Jamie is exerting with 280, so that's an even shorter arrow yet. And then we want Jose. So we're going to add Jose's arrow. So what I want is that the total of these 2 should be equal to the total of these 2. So I'm just going to approximate how far that should be. So we're going to head out to about here. And this is, Jose's force, or the force of Jose. So the 2 arrows on the right, which are the positive arrows, are balanced by the 2 arrows on the left, which are the negative arrows. And now I'm ready to go ahead and write the equation for, I'm only going to look at the horizontal motion. I'm never going to look at the vertical and horizontal motion at the same time. I'm only looking at the horizontal motion. So in this case, I know, because the problem told me, that I want the rope to come into equilibrium. So I want Jose to pull just hard enough. And you can imagine, if you're a strong adult, that maybe you would add force, and you don't want to purposely win by too much, so you're just trying to hold the line. You just want to make sure that the rope is in equilibrium. So I already know that the net force acting on this rope is 0, because of what it told me in the problem, that it was moving with constant velocity, or that it was in equilibrium. So now I'm going to start listing the forces. I personally prefer to list the forces, the positive forces first, then the negative ones. I don't like to lead off with the negative sign, but it doesn't really make a difference. I mean, if you want to put the negative 350 minus 450 first, it's still going to work out the same. But for me, I'm going to say 280 plus the force from Jose minus 450 minus 350. So let me pull together all the numbers that are not Jose's force. Over here you have negative 800, and then we're going to subtract that negative 800 from 280. So Jose's force, this is going to be minus 520. Negative 800 plus 280 gives me 520. And then to get Jose's force, to isolate Jose's force by itself, I'll just add the 520 to both sides. To find that Jose needs to supply 520 newtons of force in order to bring this rope into equilibrium. Pretty simple problem. I mean, it's really just an addition and subtraction problem, but it requires you to identify the forces and to point them in the correct direction. So while it's not very complicated math, the conceptual side of it is very challenging. These are very difficult problems to make sure that you identify the forces and get everything pointed in the correct direction. One thing just to point out before we leave this problem, though, there's nothing in this problem that said the rope wasn't moving. The rope could be moving. So the rope might just be steadily moving at a very slow speed one way or the other. When the rope is in equilibrium, it is just going to continue doing whatever it was doing at the moment when it reached equilibrium. So it might have been speeding up, but when Jose added that force and brought it to 520 so that it balanced out all of the other forces, now the rope is just going to continue to do whatever it was doing at that moment when that equilibrium was achieved. If that was at rest, then yes, it will stay at rest. But if it was in motion, then that means that that object is going to just continue to move slowly in whichever direction, or quickly maybe, but at a steady pace. It's going to move at a steady pace in whichever direction it was moving at the moment that that equilibrium was achieved. So that problem doesn't require you to identify any of the forces in particular, just the names of the people who are involved and who are supplying the force. Let's take a look at a different type of problem where you'll need to think about that particular situation and think, what are the forces? What forces would act in this situation? Some of them may be named, like I can see the thrust force is named right here, and I see it's asking about the total frictional force, but that may not necessarily be all the forces that are acting on this object. So in this problem, we're going to look at a car, Bill, driving in a car on the highway at a constant 22 meters per second. At that speed, the engine needs to produce 4,800 newtons of force, and what we want to know is, what is the total frictional force? So before I start the problem, I'm going to draw a free body diagram again to just identify what are all of the forces. And one force that should be pretty automatic, we're always going to be looking at objects that have mass, and therefore, because they have mass, they must have weight. Now the car is obviously not falling towards the center of the earth, so there must be some force that is balancing this one out to keep the car at rest vertically. In the vertical direction, the car is not accelerating, it is traveling with constant velocity, and so therefore I know these two forces must balance each other. So the weight in this case would be balanced by the force from the road. The road exerts an upward force, that's called the normal force, and I am very intentionally trying my best to draw this so that it has equal in length to the weight arrow. So those two are balanced, the car is moving with constant velocity, and that's it for that one. In the horizontal direction, I know the car obviously is capable of producing thrust because it says right in the problem that there is a thrust force of 4,800 newtons, and I know that the frictional force would always oppose the direction of the thrust. So I'm going to draw an arrow that is equal in length, and the reason I'm drawing this one equal in length is because it said that the car was traveling at a constant 22 meters per second. And this force is the total frictional force. The reason why I use the word total frictional force instead of just saying frictional force is because the total frictional force, I'm including the drag force from the air. So I'm just kind of lumping all of that together. You could draw two separate arrows. I could put a drag force arrow and a frictional force arrow. There is definitely drag force there. There's no question about that. But in general, we're just going to combine these as the total resistive force or the total frictional force. So one of the really important things about using Newton's first law or the second law is that we don't look in all the different directions at once. So I'm not going to write an equation that has all four of these in it. I'm going to focus on either the horizontal motion or I'm going to focus on the vertical motion. I'm going to treat those two completely separately, and they will act. That's a completely valid way to model the motion, is to separate the motion into what's happening horizontally and what's happening vertically. So horizontally, what I know is that the net force must be equal to 0, not because it said that it was in equilibrium, but because it said that the velocity was constant. So that is something that you must burn into your mind, that when the velocity is constant, it is because all the forces add up to 0. Now, I'm going to name the forces. I'm going to start listing the forces out here on the right side, and I'm going to do the same thing. I'm going to list the positive forces first, then I'm going to list the negative forces second. So there's a thrust force, and then there is a frictional force. And that's it horizontally. Again, only looking horizontally. There is no tension. There's no buoyant force. There's no lift force. There's no other forces acting on the car except for those four forces and these two forces acting horizontally. But I've already been told that the thrust force was 4,800. So I'm going to bring this line down and say that that is 4,800 minus f of f. So in order to isolate F of F, I'm just going to add it to both sides, and it says that the frictional force must be equal to 4,800 newtons. As a math problem, that's about as simple as it can get. It's just addition and subtraction problem, but conceptually very challenging because there was no math to even do until I created the equation that explained what was going on with this car. By identifying all of the forces with the information that I had, I was able to figure out the frictional force. So, basically, when I read this problem, as somebody who has studied physics a lot, I could just tell you right now, the answer is 4,800. I know that the thrust and the friction must be balanced because otherwise the car couldn't travel with constant velocity. But while this problem is very simple, we're going to look at more and more complex problems as we go. And this ability to draw the free body diagram and to write out the net force equation. Is the net force equal to 0 or is it not equal to 0? And we'll take a look at what happens when it's not 0 when we look at the second law. So I would like to just leave you with just one final question to think about. This is something that I would ask that you fill out on your own, that you think about this and add your responses to your notes. If you think about a situation in your car, someplace where even if you're not the driver, you've been in a car a lot, you've been in vehicles, buses, and things like that. And what I would like you to do is to think about your experiences in the car and think about examples of the first law. Think about examples of things. I'm talking about things inside the car, things like you or the objects inside your car or inside your trunk. There are times when you're driving that you will hear things moving around your car or you will see things moving in your car, even though nothing is touching them. Right? There's like kind of a mysteriousness to listening to things in your trunk sliding forward and backwards or left and right. And similarly in your car, that's the first law in action. That's the first law that's saying that of course that's what's going to happen. So I would just like you to think about one example of an object at rest inside your car that remained at rest and describing that. And then also an object in motion remaining in motion. Think about, for example, if you set something on the dash. What would happen to that object if you sped up suddenly? What if you hit the brakes suddenly? What if you turn sharply to the left or right? Think about what would happen to those objects and try to come up with one example for each of these.